Assalamualaikum. We are from Team 6 and our report is about Newton's law of cooling versus Stefan's law of radiation based on the ordinary differential equation. So there are three members of Team 6 and we will introduce ourselves based on our assigned parts. So my name is Akmal Batrisha binti Rahmat and my matrix number is 227328.
Moving on, so the reason I did this in a table to have a clear vision how I differentiate the Newton's law of cooling and Stefan's law of radiation. As you can see, this law is the law of heat transfer, but they have different types of heat transfer, which is the Newton's law is for conduction and convection, and Stefan's law is radiation, but in a form of electromagnetic waves. Okay, why it is electromagnetic waves? Because under Stefan's law of radiation, it does not require a medium. So mostly this will be applied in the space since it has a unlimited vacuum space. I'm sorry, but for the Newton's law of cooling, it is between objects and surroundings, how the heat loss from the objects and surroundings. Okay, for these both laws, they have the same type of ODE, which is the first ordinary differential equation, but the differences is that Newton's law is a linear first law of ODE and Stefan's law is non-linear first law of ODE because it requires more calculation since we need to include the numerical method and qualitative analysis. Okay, for Newton's law of cooling, it is best to apply when the temperature is low, and for the Stefan's law when it is in high temperature. This is logic because when the higher the temperature is, the more complex the equation will be. So that is how we can differentiate the usage of the equation. Okay, based on the real world application, as I have mentioned earlier, we can use the Stefan's law at the space which is high temperature, which is the stars. We can calculate the stars, the heat loss of the stars, and maybe the spacecraft heat shields, while the Newton's law is you can observe in our everyday scenarios, which is our drinks cool, how the comparison of how our drinks cool in a cool temperature and hot in a cool room and in a hot room. Okay, so this is the physics basis, which is the Newton's law of cooling is based on empirical observation, and the Stefan's law is mostly because of thermodynamics and the black body radiation history.
Assalamualaikum warahmatullahi wabarakatuh. My name is Isiwana Lina binti Nurazami. My matrix number is 229204. So right now I'm going to talk about the mathematical modeling. So first of all, we start with Newton's law of cooling. And the mathematical equation we use here is dt over dt equal to k in bracket t minus ta, which is dt over dt are rate of change of temperature with respect to time. And T is temperature, TA is ambient temperature, which is surrounding temperature, and K is a constant. And next, we talk about Stefan's law of radiation. So the mathematical equation we use here is U over A equal to sigma T power of 4. So U here is stand for total heat power emitted in watts. A is the surface area of the object in meter square. And sigma is Stefan-Boltzmann constant. And T is the absolute temperature of the object, and it must be in Kelvin. Okay, so now we talk about the principle and application of Newton's law of cooling. So first, Newton's law of cooling state that the rate at which an object temperature change is proportional to the difference between its temperature and the surrounding temperature. So this is a principle of the Newton's law of cooling. So to simplify this, we can say that a hot object cools down faster when the temperature difference between it and the surrounding is large, and the cooling becomes slower as it approaches the surrounding temperature. So now we talk about the application of Newton's law of cooling in our daily life. So first is estimating time of death in forensic science. So forensic science, they use this Newton's law of cooling to estimate the time of dead people. So second one is predicting cooling time for food or machinery in food technology. And the third one is engineering heat transfer analysis. Next is the Stefan's law of radiation. So the principle here in Stefan's law of radiation is it states that the total energy radiated per unit surface area of a hot object is directly proportional to the Ford power of its absolute temperature. So this is why in the equation we have the T power of 4. And so in simpler term, as an object get hotter, it emits much more heat energy, and increase is rapid because of the power of 4. So the application of Stefan's law of radiation is it is used to determine the luminosity of stars and other celestial body in astrophysics. So, and the second one is designing system that involves radiation heat transfer, such as furnace and insulation material in engineering.
Okay, Assalamualaikum and hi. My name is Nura Beato Adawiyah binti Runiza. My notice number is 229480 and I will be presenting about the examples. So firstly, I will be presenting about examples of Newton's law of cooling. So for the first question, which is a cup of coffee is 180 Fahrenheit when freshly poured. After 2 minutes in a room at 70 Fahrenheit, the coffee has cooled to 165 Fahrenheit. Find the time that it will take for the coffee to cool to 120 Fahrenheit. So firstly, we need to know the original formula, which is dt over dt equals to k t minus ta. So as my friend already told about this here. So next um, we need to analyze the question. So after analyze, we get to know that when there is the greater difference in temperature between the system and the surroundings, it shows that the heat is transferred rapidly. So the Newton law of cooling formula was expressed by, we need to change the formula a bit. So we got the current formula right now. So after we got the this formula, then we can after that we can solve the formula as we already got all the infos. And so for the second part of example, which is Stefan's law of radiation, the question asks us to use the Stefan's Boltzmann's law to calculate the initial value of net power emitted by the body. As I said before, we first need to know the original formula to actually use or derive the formula to become some things that we can actually use to solve the problem. So, after we analyze the question, we got to know that when a body that is not a black body absorb and emits less radiation, we get to change the equation to become U equals to E sigma A T power of 4. E stands for emissivity, which is equal to absorptive power. After that, we need to again derive the equation to become the third equation. So for the dt over dt, which is uh, the net power radiated by areas A per unit time. T naught stands for surrounding temperature. After we actually got the third equation, we can finally solve the question because all value already be given. So finally we got the final answer.
Lastly, for our conclusion, throughout all the what we have present to you, heat transfer plays a crucial role to explain this because there are slightly differences between them. As I have stated, as my teammate has stated earlier, that Newton's law is a simple calculus usage rather than Stefan's law of radiation because of the requirement to answer the complexity of the laws. This is mostly because of the differences of the range in temperature. So all in all, both laws really highlight the importance of ODE when we want to logically understand the real world problems. Okay. This I can say that mathematics, by using mathematical models, it really allows engineers and scientists to design an efficient system since it provides them an analysis and prediction of the thermal behavior visually. So for one to choose for one to create a better design, they need to have an appropriate approach of how these two laws the strengths of these two laws and the limitation that they have, so that they can provide a better design in the industrial world.
That's the end of our presentation, and I hope that all the information have been said. So thank you.